Okay, thank you. Yeah, so I'm going to talk about strength. Mainly I care about strong monads. But I'm also going to spend quite a lot of time talking about strong functors more generally. And the point of this is that there's a bunch of results about strength that I proved with Tamo, some of which are kind of already known in various levels of generality, some of which seem to be somewhat folklore. But yeah, we're kind of tidying up the literature around strength, really. So let me start by motivating strong monads, in case you haven't seen them. So here's some Haskell code at the top. It uses a list monad. It doesn't matter what it does, but it uses a list monad in some way. And we can think about what this means kind of in category theoretic terms. So there is a list monad on the category of sets, for example. So list over X is a set of lists, just a set of lists over X. And in particular, given any function from X to list over Y, we get a function from list X to list Y. This is the classic example, the bind of the list monad. And in this outer bind here, so where we have this bind lambda X, the lambda X is a function which takes an int and gives us a list of ints. And if we do bind of this, we get a function from list of ints to list of ints, and we can pass it this list 1, 2, 3. The inner bind is slightly different though. So on the inside, this lambda y is not a function from int to list of ints, because it has a free variable x inside it, right? So really, it's more like a function from int times int to list of ints. And when we say bind of this function, we really want a function from int times list int to list int. Right? We want to just pass around this extra int and just do nothing special to it. So this means we want a more general form of price extension where we have this gamma, and this gamma we just pass around and don't do anything special to it. And this is not the price extension of an ordinary monad anymore. This is now a strong monad, right? Which is really more in category theory than having a monad. So in general, strength is there just so we can pass around free variables, really. So what I'm going to talk about is some kind of natural questions that arise when we talk about strength. So one question is, if we have, say, a monad, when can we actually construct a strength for it? When can we actually make it into a strong monad? And if we can make it into a strong monad, when is the strength actually unique? When is there actually only one thing we can do with gamma? And another thing that comes up is there are several different definitions of strong monad or strong functor, and these all give us kind of these all lead to kind of nice results about strength. So I'm going to talk about these things. First, I'll start by giving the definition of strong functor, and to do this, I'm going to do this in quite a lot of generality, more generality than I really need, but I want to talk about actions at some point, so I might as well introduce them now. So we suppose in general that we have some monoidal category B. This you should just think of as a Cartesian category, so sets with products or something like this. And then an action of B on some category C. And again, think of this as just a Cartesian product or something like that. So we could have B is equal to C, and both this triangle and this tensor are just products of sets. And in particular, we require this triangle to be unital and associative in some way. So the easiest example is sets. Any other Cartesian category will give us an example. So we could use posets instead. We could use pointed sets and point preserving functions. And also this other example, which is, so we have this category n comma set, where objects are pairs of a set and an endo function on that set. And morphisms are just functions that preserve the endo functions. And then this category just has products where we just take the products of sets and do the component-wise. These examples will demonstrate a few different things about strength. Okay, so all of my examples are just Cartesian categories for this talk. I really don't need this much generality, but I want to mention actions for another reason. Okay, so one thing that will come up a lot is morphisms of this type. So a morphism from gamma triangle x to y. This you should think of as like a map from X to Y in a context gamma. And in particular, we have identities. So we have maps from X to X in context I. And we can compose these things. So if we have a map from X to Y in context gamma and a map from Y to Z in context gamma prime, we get a map from X to Z in context gamma prime tensor gamma. Okay, so now what is a strong functor? So a strong functor, so if we have that V acts on two categories, C and D, then a strong functor from C to D is an assignment on objects. So given any object of C, we get an object of D. And then given any map from X to Y in context gamma, we want a map from f of X to f of Y in context gamma. And this would require it to be natural in gamma and to preserve identity and composition in the sense that I had on the previous slide. And the first observation about these is, firstly, we do get an ordinary functor from C to D, essentially just by saying, consider maps in context I, which are really the same thing as morphisms from X to Y. So an easy example is the functor, the list functor, which goes from set to itself. There we just say, given a function f from gamma times X to Y, and some element of gamma and a list over X, we just map over the list. And the element of gamma we just pass to the function every time we use it. So we don't do anything interesting with gamma, we just pass it to the function. Another example would be, so take this category n comma set, so we have endo functions on sets. Then one functor we could define is taking products with natural numbers. And on morphisms, we can say, well, just do nothing interesting with gamma. So just pass gamma to X, exactly as we did for the list functor. But we can also do something else, which is actually apply E a bunch of times to gamma. Right, so we can actually use E to the n of gamma instead of just gamma. And the point is, this is still a perfectly good strong functor. And the ordinary functor that we get from this is the same as, so the ordinary functors we get from these two are exactly the same. They're just kind of the ordinary functor that takes products with natural numbers. Okay, there is an equivalent definition of strong functor, the more usual definition, really, where we say we just have an ordinary functor and we equip it with some strength, where a strength is a natural transformation of this type, which satisfies some properties that related to the action. So in particular, in this case where we take products of natural numbers, we have two different ways of defining the strength. One where we just do nothing interesting to gamma. Another one where we say do E to the n of gamma. The point I want to make here is that strength is not a property of a functor. Right? Strength is some extra data that we have to provide. And in general, there are multiple ways of providing this extra data. Okay. So this leads to kind of the first natural question to ask, which is when are strengths actually unique? And it turns out they are unique in quite a lot of cases. So the first thing to notice is that if we have a map from X to Y in context gamma, we can, in a sense, apply it to points of gamma. So a point of gamma is just a morphism from I to gamma. And given any one of these morphisms, we get a morphism from X to Y. And in fact, because of the laws our strength has to satisfy, we can say exactly what it must do on points. On points of gamma, it must satisfy this equation. So it's completely determined on points of gamma. And this immediately tells us that if every morphism is determined by points of gamma, then in fact there is only one possible strength. Right? It's just the unique morphism, if it exists, it satisfies this property. So in fact, if we have a morphism that satisfies this property for every gamma and every X, it will always be a strength and will always be the only possible strength. So for example, in the case of sets with Cartesian products, every functor has a unique strength, and we really can't do anything with gamma. We just pass it along. This also gives us a way of proving that strengths don't exist. So for example, if we take posets, there is a functor from poset to itself that just sends a poset to its kind of underlying sets, just discretely ordered. And it turns out, in this case, we still have well-pointedness, which means strengths, if they exist, must satisfy, the strengths, if they exist, are unique. And in particular, from this equation, we can figure out that a strength must just do this for this functor. But this is not a monotone function, which means there is no possible strength. Okay. So now let me move on to the kind of dual question, which is when do strengths exist? And we can talk about the same sort of thing we can talk about applying maps to points. And we can say that if we have any function zeta, which kind of behaves as though we're just applying a map to a bunch of points, so sends any point to a morphism from X to Y. If we can convert any one of these to if we can convert these into maps from X to Y in context gamma in some coherent way, which means some naturality gamma, some respecting the action, then every functor has a strength. Then every functor becomes a strong functor. The point is, the idea is we just take this equation that says the strength doesn't points and just take that as the given zeta. And then use this phi to just convert it into a morphism. And that will give us a strength. Also in a coherent way. So if we assign a strength to every functor in this way, then it turns out that every natural transformation will preserve strength in the appropriate way. So again, this works fine on sets. And we get kind of this unique way of making every functor into a strong functor. This also works, for example, if we take pointed sets. In pointed sets, the situation is a bit stranger, though. So in this case, a morphism from I to gamma is actually exactly one of them. And it's just the distinguished point of gamma. Which means one of these zetas is just a choice of a morphism from X to Y. And then there's actually only one way of defining this phi of zeta. So all we can do is take zeta and apply it to the unique points, and this gives us this gives us a function from X to Y that tells us what to do with X. This is really the only way of defining this. But this does mean that every functor can be made into a strong functor. And in this case, we find that we actually completely ignore gamma and just send it to star. But this is really the only way of coherently creating strengths for functors on pointed sets. Okay, so now let me move on to strong monads. So the definition, my preferred definition looks like this. So we start with some category C with an action. And a strong monad is first an object mapping. So and given any object of X of C, we get an object T of X inside C. And we have a bunch of unit morphisms that go from X to T of X, exactly as a normal monad. And then we say, well, for every map from X to T of Y in context gamma, we get a map from T of X to T of Y in context gamma. This is required to be natural in gamma and also to satisfy free laws, which are really analogous to the normal monad laws. Okay, so list is an example. So we just say, well, eta is singleton, like as we normally do for the list monad. And the class extension is just really the class extension of the normal list monad, except that we just kind of pass through this gamma. Again, we don't do anything interesting with gamma. Okay. And then we can also extend this case where we take products of natural numbers to two strong monads on this category n, set. So both of them, they're pretty similar, and if you've seen a writer monad, then these are really both writer monads. And again, the difference is that either we just don't do anything to gamma, or we apply E a bunch of times to gamma. And both of these are perfectly good strong monads. Right, so again, strengths are not unique, even for monads. There are actually quite a few equivalent ways of defining strong monads. So a more standard one would be to say, well, we have a strong functor together with a unit and a multiplication. And the unit and the multiplication have to be compatible with the strength. Another one which is quite nice is we can say, well, firstly, we have a monad, and also a listing of the action to the Kleistli category of the monad. The idea here is that if we define this action on the Kleistli category of the monad, well, you can think of morphisms inside the Kleistli category as computations from X to Y. And this action would give us a way of talking about computations from X to Y in a context gamma. Right? And also composing these things and having identities for these things. This is also the sort of thing that you'd want to do if you have a fried category, for example. So again, we can ask the same questions about uniqueness, existence, that sort of thing. Uniqueness is actually pretty easy. So we just do the same thing that we have for uniqueness of strong functors, and it just works perfectly for strong monads as well. So if the action is well pointed, strengths are unique whenever they exist, even for monads. Existence barely works at all, in fact. So if we have one of these spies that assigns, assigns strengths to functors in a coherent way, it turns out these very rarely form strong monads. So in fact, if the strength that we assign to the identity functor makes the identity into a strong monad, then the action must have been well pointed. So there aren't many situations in which this happens at all. So out of the examples I gave, this only occurs for sets. It does not occur for post set or for pointed sets or anything like this. So for example, in pointed sets, we end up with a strength that just discards gamma and just converts it into star. And this does not make the identity into a strong monad. Okay. So there's something that I want to talk about relatively briefly, which is, well, so far I've focused on actions of monoidal categories. There are really several equivalent ways of getting kind of like strength-like notions. Equivalent ways of talking about maps from X to Y in a context gamma. So one of these things is enrichment. The point is now that we have some kind of, for every X and Y, we have some kind of object of V, which represents maps from X to Y, kind of internally inside V. And there is a nice connection between actions and enrichments. So the point is, if we have a bunch of adjunctions like this, an adjunction like this for every X, so on the left we have an action-like thing, and on the right an enrichment-like thing, then making this triangle into an action is the same thing as making this arrow into an enrichment, such that this isomorphism condition holds. This condition is effectively saying, this condition says, in the enriched sense, that the actions form copowers. Copowers of V on C. Okay. And then we can kind of transfer the definitions of strong functor and strong monad along this bijection. And we get the definitions of enriched functor and enriched monad. So an enriched functor says, well, for every object of C, we get an object of D. And also we have morphisms like this, which go from X arrow Y to F of X arrow F of Y. Preserving identities and composition in the right way. And we can do a similar thing for monads, where in particular we get these morphisms bind, which go from x arrow ty to t of x arrow ty, satisfying three laws, which are the monad laws. One thing I want to say about this is that this is really the sort of definition we have inside Haskell. So the point is that inside Haskell, fmap is really a family of functions, like internal Haskell functions. And also bind inside Haskell is a family of functions, really of these types, right? Really matching the kind of enriched definition. And this is really why we don't have to talk about strengths explicitly inside Haskell, why we don't have these explicit gammets, because kind of everything is happening internally, just as is happening in this enriched sense. Okay, that's really all I wanted to talk about. There are a bunch more results inside the paper, which I won't mention in any detail here. So in particular, there is also a third way of looking at strength, where we have kind of adjunctions but on the other side. These also lead to some equivalent definitions of strong functor and of strong monad. And they also lead to some more results about strength. So in particular, they lead to some story about strong monads and kind of liftings to categories of algebras for the monad, which are quite nice for various things. There's also some story about commutative monads, which I won't explain here, but we have this inside the paper. But that's it. That's all I want to talk about.